So we were talking about potential energy. Potential energy is energy possessed by an object due to its configuration. The configuration could be depending on change in position or change in its shape. So there are two types of potential energies. One is gravitational potential energy, and the other one is spring potential energy. And in some cases, instead of spring, we may also have elastic rubber band. So for that, we use the term called elastic potential energy. Okay. So it could be either spring or elastic potential energy. So when you stretch a rubber band, you store some energy in it, and that energy is elastic potential energy. Likewise, when you stretch a spring, you store some energy in the spring, and that is spring potential energy. In case of gravitational potential energy, you lift some object above the ground. When you do that, you will store some energy in the object, and that stored energy is gravitational potential energy. Okay, it's the stored energy. Like in chemistry, you might have seen chemical potential energy, which is the energy stored in a battery or something like that. So that's different thing. So we don't need to worry about that here. But here we'll only talk about gravitational potential energy, which is the stored energy due to change in the height, and spring potential energy, which is due to stretching of the spring. Okay. So and the energy in this case is given by this formula mgh, because it depends on the height, how high you raise the object. So this gravitational potential energy is mass times acceleration due to gravity times h. It is denoted by letter u. Okay, potential energy is denoted by u, or sometimes you will also see Pe for potential energy. So mgh, where h is the height of the object. If it is on the ground, then here h is 0, so there is no potential energy. So Pe 0. Here at some height, it will have some potential energy. Here in this case, potential energy is given by 1/2 spring constant times change in the distance squared, okay, extension squared. You may also see delta x here. Actually, if you want, you can write delta x. So potential energy in this case is 1/2 spring constant times change in distance due to the stretching, and square of that. So that's change in length. So that's about the two types of energies we talked so far. So we have talked about kinetic energy, okay, which is 1/2 mv squared, and here we talked about potential energy. Potential energy is mgh, or if it is spring potential energy, then it's 1/2 k delta x squared. And the sum of kinetic energy and potential energy is called mechanical energy. So when you add these two, it's the mechanical energy. And the law of conservation of energy states that if there is no loss of energy, then energy remains conserved. Okay? There is no loss of energy, or there is no decrease in energy. So energy is conserved, and the meaning of that is energy can neither be created nor be destroyed. But it can transform from one form to another form. Okay. So what that means is, let's say you drop an object from some height. Okay, so that's the initial position of the object, and at this position all it has is the potential energy. Okay, because it has some height, that means it has potential energy, and it starts at rest, so it doesn't have any kinetic energy. So kinetic energy is 0, and the reason for that is because speed is 0. Kinetic energy depends on speed. If speed is 0, kinetic energy is 0. Now as you drop this object, what happens is it will gain speed. Okay, it gains speed and it loses the height. Now it loses height means potential energy would be less than here, but there would be greater kinetic energy. Okay, so it will have some kinetic energy and it will have potential energy. There will be decrease in potential energy, but increase in kinetic energy. As it falls, there would be further increase in kinetic energy because of increase in speed, and there will be further decrease in potential energy because of decrease in height. Okay, so height goes down, potential energy goes down. Speed goes up, so kinetic energy goes up. And finally, before it hits the ground, the height is 0, so that means all the energy would be converted to kinetic energy. Okay, so potential energy would be 0. So here initially all the energy is in form of potential energy, and then you have part kinetic, part potential, part kinetic, part potential, and then all kinetic. Okay, so if you start with 1000 joules, here if you total that, you'll still have 1000 joules. Here if you total these two, you'll still have 1000. Here still have 1000. So the total energy doesn't change. What changes here is the form of energy. So here all the energy is 1000 potential. Here you may have 700 potential and 300 kinetic. Here you may have 700 kinetic and 300 potential, and here you have all kinetic. Okay, so that's what this means. You cannot create or destroy energy, but you can simply transform from one form to another form. So this thing is called conservation of energy. Okay. So let's look at conservation of energy problems. Did I give you worksheets? Anyone needs worksheet? So let's look at number 1. So the person is holding a rock at some height. Oh, sorry. Yeah. Oh, I forgot to put that on. Did I have that on Blackboard? Okay, so let me real quickly add this on Blackboard. Okay, so just a minute. Okay, so those who are on Zoom, you can download that from Blackboard. I just uploaded that on Blackboard. So please read the question. So while people are downloading this, I just want to remind you one thing. So usually I talk with individual students after test to go over their test and talk about how you guys are doing. So I didn't get a chance to do that after the first exam. So I will be posting a schedule sheet on Blackboard sometime this afternoon. Please put your names, okay, for the meetings. So we'll be meeting from next week, from Monday, to go over your test and then talk about how you are doing overall in this course, and if you're not doing well, then what you need to do, okay, all those kinds of things. Okay, so let's look at this problem. So initial height is 3 meters. Calculate the rock's velocity when it falls to 1 meter above the ground. So conservation of energy. So conservation of energy is, so let's say the initial position of the rock is here, let's call that 1, and then we want to find the speed of the rock at point 2. Okay. So mechanical energy is always conserved. That means potential energy plus kinetic energy at point 1 would be equal to potential energy plus kinetic energy at point 2. Okay, assuming that there is no energy loss. So what's the potential energy at point 1? At point 1, potential energy is mass, g, and height. Okay, height at 1. What's the kinetic energy at 1? 1/2. The formula for kinetic energy is m speed squared. Okay, I'm using the soft script to denote that this is for point 1. And potential energy at point 2, the formula for potential energy is mg at point 2, it's height 2, plus formula for kinetic energy, 1/2 mass times speed at 2 squared. Okay. And initially the rock is at rest. So, the person is holding the rock initially, so it is at rest. That means this thing is 0 because velocity is 0 or speed is 0. So, we want to find this, okay, or velocity final. So, to find that, let us subtract mg h2 from both sides. So, mg h2 minus mg h2, mg h2 plus 1/2 mg v2 squared minus mg h2. Okay, I am just subtracting this on both sides. So, then you can cancel this. No, sorry, you can cancel this and this. So, and then, so you have m and g common on both the terms. When you have the terms common on both the terms, you can pull it out of the parentheses. So, what is left is h2 minus h1. On the right side, we have, I cancel this and that. So, we have 1/2 m v2 squared. Again, I want to find v2, so I need to do the rearranging of the terms here. So, I need to get rid of half. So, to get rid of half, I will multiply both sides by 2, and I also need to get rid of m. So, I will divide both sides by m. So, can cancel 2 and 2, m and m, m and m. So, 2 g h2 minus h1 is equal to v2 squared. So, we want to get v2. To get rid of square, you need to take square root on both sides. So, 2 g h2 minus h1. Okay. So, we got the expression. Now, plug in the numbers. 2 g is always same. So, it is acceleration due to gravity. Now, initial height is 3 meters and final height is 1 meter. So, that will give you the speed as it falls above 1 meter from the ground. So, you can do that calculation. I will let you guys do that calculation. Now, let us look at number 2. Number 2 is also similar kind of problem. It is about the conservation of mechanical energy. So, a dart of mass 0.1 kilogram is pressed against the spring of the toy dart gun as shown in the figure on the right. So, it has the dart gun has spring which is initially compressed. So, whenever you compress a spring, you store potential energy in the spring. Okay. So, there is stored energy in the spring because it is compressed. Compressed spring has spring potential energy. And then when you release that, it releases the potential energy. Okay. And then the dart would be pushed in the forward direction. So, here the dart is at rest. Okay. So, this whole thing is our system. the spring and the dart. That's our system here. That's our system. Okay, and the total energy in this case would remain conserved. Okay, so whatever total energy you have here, you will have the same energy here, because there is no loss of energy in this case. Okay, we assume that there is no energy loss, the energy is conserved. So let's say that this is state 1, and let's say this is state 2. You don't have to say that, I'm just giving a name for the state. Okay, you can just say 1 or 2, 1 and 2. So total energy at state 1 is equal to total energy at state 2. Okay, so this is from conservation of mechanical energy. So what are the energies in the system? So the system has kinetic energy and potential energy, that's the mechanical energy. So this is at state 1, this is at state 1, and then total energy at state 2, kinetic energy at state 2 plus potential energy at state 2. So in state 1, the dart and the spring both are at rest. That means what's the kinetic energy? By the way, in this case, the potential energy we are talking here is not gravitational potential energy, but it's spring potential energy. Okay, so the formula for spring potential energy is 1/2 delta x squared. Okay, that's for state 1. So let's just say 1. Kinetic energy 1/2 m v2 squared plus potential energy is 1/2 k delta x 2 squared. So that's the total energy. That's the total energy for state 1 and 2. So what's the kinetic energy of this system when it's compressed? 0. Yes, because there is no velocity or speed. Okay, and here what's the, so when you release the spring will go to its equilibrium state. When it's in equilibrium state, now it's no more compressed, it will have its original length. Okay, so here the spring will have no energy, no spring energy. So delta x is 0, no more stretched or compressed. So that means potential energy is 0. So this would be 0 for the released spring. Only the compressed or stretched springs have potential energy. So let me write it down so that you don't confuse that. So let's say you have spring. This is the original spring, original shape of the spring, not compressed, not stretched. Okay, so in this case, spring potential energy, let me write it as u spring is 0. When you stretch it, so now you will have potential energy. Okay, 1/2 delta k, so no, k delta x squared. This delta x is how much it is stretched. Okay, or you can also compress the spring instead of stretching. So you are compressing it, and when you compress it, it will have potential energy. Okay. In both compression and elongation, you have potential energy, but if it is in its original state, then there is no potential energy. So, when you release the spring, it comes to its original shape, so there is no potential energy. So, this potential energy would be transferred to the kinetic energy of the dart. So, dart would be moving forward. That is what this is. So, what we want to find here, what's the speed of the dart? We want to find that. Okay. So, let us do that. We have 1/2 k delta x squared 1/2 m v2 squared. You can cancel 1/2 and 1/2 on both sides. If you do not want to do the directly like that, you can multiply both sides by 2 and then cancel 2 and 1/2. So, how would you find v from this expression? Why don't you guys write down the expression for v from this and tell me what the expression is. So, what did you get? V2 is equal to square root of delta x squared, okay, over m. Okay, that's good. So, k is the spring constant of the spring, which is 250 newtons per meter. There is a typo there, that is per meter, 250 Newton per meter. And by how much the spring is compressed, that is delta x. Yeah, 6 centimeters. 6 centimeters. So, we need to change that to meters. So, that is times -2 would be in meters. And then do not forget this squared. Okay. So, we have squared for delta x. And mass of the dart 0.100 kilogram. Okay. So, you do the calculation. That will give you, let us see, 250 50 times 6, is that 0.3 meters per second maybe? 3 meters per second. So, it should give you 3 meters per second. Okay, now let us look at the next one. Number 3. At the county fair, Katie tries the water slide, whose shape is shown in the figure. The starting point is 9 meters above the ground. So, this starting point is, the height is, initial height is 9 meters. She pushes off with an initial speed of 2 meters per second. So, her initial speed V initial, or let us say V1, is 2 meters per second. and the slide is frictionless, so that means there is no loss of energy, so energy is conserved. And we want to find how fast Katie will be traveling at the bottom. So here on the bottom, what would be her speed? Let's say that's v2. So her initial speed is 2 meters per second, and we want to find her final speed. So let's say this is 0.1, that's 0.2, and here energy is conserved, so mechanical energy is conserved. Okay. So what we want to write the mechanical energy at this point and mechanical energy at that point. So mechanical energy at 1 is kinetic energy 1 plus potential energy 1, and mechanical energy at 2 is kinetic energy 2 plus potential energy 2. Okay, that's conserved, no loss of energy. Let's see. You're looking for something here? No? Okay. Okay, so let's write down the formula for kinetic energy and potential energy. So kinetic energy is 1/2 mass times speed squared, and the speed is at 1, so let's write that as 1, because I don't want to use the same letter for final and initial, so I need to differentiate final and initial. Potential energy is mass times g times height. Again, I want to differentiate the height, so let me write it as 1. Kinetic energy at 2 is 1/2 mv2 squared. Potential energy at 2 is mgh2. Okay, so 1/2. All these terms have mass. When you have mass on all the terms, when you have a variable on all the terms, you can actually cancel that, okay, get rid of that. So cancel m, all. So v1 is 2 meters per second squared plus g is 9.8 meters per second squared. That's always true. Height, initial height is 9 meters. 1/2. That's what we want to find. So v2 squared plus, what's the final height? 0, yeah. So that means this is 0. So let's do the math. So I want you to find v2. Okay. So this would be 2 squared, give you 2 plus 9.8 times 9. What's that? Sorry? 88.2. That is equal to, and then multiply both sides by 2 to get rid of 1/2. And then v would be square root of 2 times 90.2. Is that 13.4? What's that? 9? got 13? Yeah, I also have 13.4. So 2. So take square root of 180, what do you get? Yeah, 13.4. So 13.4 meters per second. Okay, that's the speed on the bottom of the ramp or the water slide. So let's look at number 4. Four is exactly same as this one, a little bit different, but the concept is exactly same. So you have this roller coaster. So let's say the position of the roller coaster here is 1, the position of the roller coaster here is 2, and the position of the roller coaster here is 3. Okay. And again, here the energy is conserved. So that means potential energy plus kinetic energy at 1 is equal to potential energy plus kinetic energy at 2, which is also equal to potential energy plus kinetic energy at 3. Conservation of energy. Okay. So to find the speed of the roller coaster at the bottom of the hill, let's only use these two. Okay, we don't need to use all three. So for part A, just use that. So potential energy at 1 is mg h1. Okay, that's the height. That's the height, plus kinetic energy at 1/2 m v1 squared. Potential energy at 2 is m g h2. Kinetic energy at 2 is 1/2 m. Okay, let's write uppercase m v2 squared. So we want to find v2. And it says that at 1, the roller coaster starts at rest. Okay, so that means this is 0. Starting is at rest. So we want to find V2. So to find V2, you can subtract mgh2 on both sides. mgh1 minus mgh2. mgh2 plus 1/2 mv2 squared minus mgh2. Okay, I'm subtracting this one and this one on both sides. So this and this cancel, and then multiply both sides by 2, and then also divide both sides by m to get rid of that m. So then V2 squared would be 2 over m. I have m and g common on both the terms, so I can pull it out, m and g. Okay, so mg and mg pull out of the parentheses, and what's left in the parentheses is h1 minus h2. Okay, I can cancel this m and that m. So then we'll have 2g h1 minus h2. So to find V2, I need to take square root on both sides. Okay, so square root 2 times g is 9.8, always same value. Height 1, 40 meters. Oh, by the way, this height is from this bottom, okay? So from here, not from this one. So we consider this to be zero height. So this is h1 is 0 here. So from here to here, this height is 40 meters. So h1 is 40 meters, and h2, so this is h2, sorry, is 0. The final height of the roller coaster is 0. So do the math. 2 times 9.8 times 40, and take the square root of that. 28 meters per second. Okay. And it's asking how high will it go on the third stage. So again, same thing, we use the same equation. So for the third stage, we need to use this part because that's what the energy is at stage 3. So you can equate this one with this one, or this one with this one, whichever you want. Okay, so I'm going to equate that with the first part. So I'll use this one, PE1 plus KE1 is equal to PE3 plus KE3. So we are looking for H3 here. So PE1 mg H1, KE1 is 0, there is no speed in the beginning. PE3 is potential energy at 3, which is mg H3, and kinetic energy, what's the kinetic energy at 0.3? It says at what height will it have half this speed? So 1/2 m, the speed at h3 would be half of that, which is 14. So 14 meters per second squared. Okay. So here at this point, speed is 1/2 that of 28 meters per second. So we want to find, so here also we have m on all the terms, so you can cancel m, m and m. So we have gh1 left here, and then you can take this gh3 to the left. No, actually I don't want to do that, because we are finding H3, so you want to take this thing to the left, minus 1/2 14 meters per second squared. Okay, I'm taking this thing to the left because I want to find this in terms of H3, and to find H3 I need to divide both sides by g. Okay, so divide both sides by g, or you can do that later. Okay, so let's first find this left side. So this g is 9.8 meters per second squared. Height at 1, we already used that, 40 meters, minus 1/2 times 14 squared. Okay. So do the math and tell me what H3 is. What's that? Yes, 30 meters. Okay, so that's that. We'll 20 meters. What do you mean?
If you just think about it logically, you think of it like 20 meters, since you're half the velocity going
So
30 just because the relationship from kinetic energy to 30.
yeah, so here basically some of the potential energy is, some of the kinetic energy is converted to potential energy in this case. So here you have most of the energy is in form of potential energy, and all of that is converted to kinetic energy at that point, because there is no potential energy here. And here part would be kinetic and part would be potential. So here, did we find the total energy? We didn't find the total energy, otherwise I can show you how much energy we have here. I mean, you can find the total energy here. So 40 times mass times mass is not given, although.
The potential energy at 1 is 392.
How do you find that? But do we have M? No, you cannot find energy in this case because we don't have M. But again, the energy is just transformed from one form to the another form. Okay, so here you have part kinetic and part potential. But if you go all the way to 40, I didn't draw the picture very correctly here. So if you draw a little bit higher here, I should have drawn this 3 here actually. Okay. If you go all the way here at the same level as 1, then what would be the energy at that point? It would be same as the energy here, right? Or in other words, I can ask you how high will it go before it comes to rest? As high as that one, right? Because the energy is still there. I mean, I usually show lots of demos in class, but now because most of the people are on Zoom, so I cannot show you demos, unfortunately. We have really nice demos that shows how the energy is conserved. Maybe we can, I can show you that in next class. Okay. So we have a minute left. If you guys have any question, I can answer your questions. Otherwise, I think we are done. Have a great weekend, and we'll meet again next week. And please do not forget to sign in the meeting schedule sometime this afternoon. 9.6 meters per second on number 3. So let's see. So 1/2 speed is 2, g is 9.8, height is 9. That's 0. So this is 2 squared is 4. And 4 divided by 2 is 2, so that's 2. And 9.8 times 90 is 88.2. And to get rid of that 1/2, I'm dividing both sides by 2. So we have v squared. To get rid of squared, I took square root on both sides, so that's 2 from here. And 2 plus 88.2 is 90.2. And 90 times 2 is 180. So if you take the square root of 180, you get 13.4, I think. Square root of 180. Yeah, so 13.4, that's how I got.